Welcome to the deep dive. Today we are opening up the sources to tackle a concept that's really changing software development. I mean, it's radically altering the conversation around business risk.
Right.
We're talking about security scanning and the whole philosophy known as shifting left.
Yeah.
And our mission today is to, unpack this. We want to give you a shortcut to understanding not just the what, but the why. How these tools are fundamentally transforming the role of every single developer.
And it is so timely. I mean, security just can't be an afterthought anymore. We've all seen the chaos of a zero-day panic, right? The late-night alerts, the scramble to patch everything.
Oh, absolutely.
For decades, security was, it was treated like this final hurdle, a painful compliance check at the very end of the line before a release.
And that's the old model. It's incredibly inefficient. So what's the real, the business-driven argument for this shift left idea? Why move security checks to the very beginning?
It's all about cost. It's a massive economic difference. I mean, studies consistently show that a vulnerability you find and fix during development costs something like 30 times less to fix than one you find in production.
30 times. Wow.
Yeah. If you find a hole in your boat before you leave the dock, you just patch it. It's easy. But if you find it out in the open water, you're in a full-blown crisis.
That makes perfect sense.
So shifting left just moves that security audit from, say, a once-a-month headache to an instant feedback loop that runs every single time you commit code.
Okay, so if we accept that premise that the feedback has to be immediate, that takes us right to the tools. We see all these acronyms: SAST, DAST, dependency scanning. Let's start with that classic 1-2 punch for application code, SAST. What is it actually doing under the hood?
So SAST stands for Static Application Security Testing, and the key word there is static.
Static.
It operates without ever executing your code. It doesn't need a running application, which is its biggest advantage.
So it's just looking at the raw source code. We use the analogy of like a superpowered spell checker. Is that fair?
That's a great way to start thinking about it, yeah.
Yeah.
But it's actually a lot more sophisticated. It analyzes the code's abstract syntax tree, the AST. It's mapping out every possible path that data can take.
I see.
And by analyzing that structure, it can spot patterns that look like SQL injection or, cross-site scripting. It's the grammar police for vulnerabilities, checking the code's construction before it's ever even run.
And its strength is speed then.
Speed and coverage. It can scan the entire code base very, very quickly.
But that speed has to come with a trade-off, right? If it's only looking at the structure, it must miss things that only show up when the application is actually running.
That's the critical trade-off, absolutely. Yeah. And that's why you need the second punch. SAST is fantastic at what it does, but it can struggle with, say, complex configuration issues. And it's famous for false positives.
Ah, right.
Because it assumes a path could be exploited, it might flag something that isn't a real threat in your specific environment.
Which brings us to DAST. So if SAST is the static grammar check, DAST, dynamic application security testing, that must be the actual test drive.
It is, yeah. It's the real test drive. DAST requires the application to be running, usually in a secure, isolated environment. A review app is a common term for it.
Okay.
And instead of looking at the code, it attacks the application from the outside, just like a hacker would.
So when you say it actively tries to break in, how does it do that? What's the mechanism there?
Well, a common technique is called fuzzing. DAST tools will just flood the application's inputs, forms, URLs, APIs, with all sorts of malformed or unexpected data.
Just throwing junk at it to see what happens.
Exactly. And it watches how the application responds. Does it crash? Does it return an error message that gives away too much information? SAST would never see that because it only ever saw the original clean source code.
That really makes the 1-2 punch idea essential then. SAST gives you that internal speed, and DAST provides the real-world runtime validation.
You need both.
But there's a cost, isn't there? I mean, running a full DAST scan means spinning up a whole review app for every single merge request. That sounds like it could create friction, maybe slow things down.
It does introduce complexity, absolutely. You're trading some of that speed for accuracy. Your infrastructure has to be pretty robust to spin up those temporary environments quickly. And if a DAST scan takes 30 minutes to run, developers get frustrated fast.
Okay, so that covers the code we actually write. Let's move on because modern apps are so much more than that. What about the things we, accidentally leave in? The API keys, the passwords.
Ah, the oops moment. Yeah, this is the domain of secret detection, and it is, I mean, it's absolutely non-negotiable in a modern pipeline.
And the problem isn't just that it's in the code, right? It's that it gets into the history.
Exactly. People think if they delete a password from the code and commit again, it's gone. It's not. It lives forever in the Git history. The exposure is permanent.
So the real goal isn't just to find the secret, it's to stop it from ever getting into the repository in the first place.
Precisely. And the best systems now use what's called secret push protection. It's a critical feature. It actually intercepts the git push command before your code ever hits the server.
A preemptive block.
A hard stop. It scans the changes you're trying to push, and if it sees something that looks like an AWS key or a password, it just rejects the push. The mistake is stopped before it even happens.
It's a huge stress reducer.
Yeah.
So, okay, that's secrets. Now what about all the external code we use? The third-party libraries. I mean, nobody builds from scratch anymore.
And we inherit so much risk with every NPM install. This is where dependency scanning comes in. The concept is pretty straightforward.
Okay.
The tool reads your manifest files, your package.json, your gem file, whatever you use, and it checks every single library and its version against a massive database of known vulnerabilities.
So it's like scanning your supply chain for known issues. Can you give us an example of why this is so important?
The perfect example is Log4j, the Log4 shell crisis from a few years back.
Oh, everyone remembers that one.
It was a single tiny logging library used everywhere. The flaw wasn't in your code, it was in the code you imported. Dependency scanning is designed to catch exactly that kind of thing.
So the second that Log4j vulnerability hit the public databases, a good dependency scanner would have started lighting up like a Christmas tree on every project.
Immediately. And the feedback is so specific. It doesn't just say you have a problem. It says you're using Log4j version 2.14 Soro, which has this critical vulnerability. Upgrade to version 2.17.1 to fix it. It's actionable.
That brings us to the payoff then. We've got all these scans running, SAST, DAST, secrets, dependencies. But if the reports just land on some security person's desk, we haven't really shifted left, have we? How does this get back to the developer?
And that's the absolute core of it. The whole shift is realized in the merge request. The main benefit is something called the security widget.
Okay.
When the pipeline finishes running all these scans, the results are summarized and presented right there in the merge request view.
So no more waiting days for a security review. The person looking at the code, the reviewer, sees the impact of the changes instantly.
Instantly. The widget will say something like, this branch introduces 5 new vulnerabilities, 2 critical, 3 high. It changes the ownership of the problem. Security becomes a shared responsibility right there in the code review process.
So the human reviewer doesn't have to be a security genius.
Exactly. The tool flags the technical security issues. The human can focus their valuable time on, the code logic, the architecture, the stuff a machine can't check.
But what about enforcement? What happens if a developer does introduce a critical vulnerability? Can you actually block them?
That's the difference between just reporting and actual governance. The best tools let you configure merge controls. You can set a policy that says, for example, a branch cannot be merged if it introduces any new critical vulnerabilities.
So the merge button is literally disabled until the developer fixes that issue.
It's disabled. It's automation applied to governance. It removes the need for a human to be the bad guy, the gatekeeper. The policy is the gatekeeper.
That's powerful.
Yeah.
Okay, so we have this immediate feedback in the MR, but what about the bigger picture? For management, for compliance, you need more than just what's in a single branch.
You do, and that's where the full vulnerability report comes in. If the MR widget is the micro view, the vulnerability report is the macro view. It's the single source of truth for the entire project's security health over time.
So a security lead could look at that and see trends.
Exactly. They can ask, are we fixing high-severity issues faster than we're introducing new ones? What's our average time to fix a critical bug? It shifts the conversation from just fighting fires to strategic risk management.
So the two things work together. The MR widget drives the day-to-day developer behavior, and the big report informs the high-level strategy.
That's it. It's a culture change, really, driven by immediate and actionable automation.
Okay, so for you, the learner, taking this deep dive with us, let's just quickly revisit the 3 big ideas that bring all this together.
Right. First, SAST versus DAST. Remember, SAST is the fast static code check, and DAST is the slower, dynamic running application check. You really need both.
Second, the power of prevention. Tools like secret push protection and dependency scanning don't just report problems, they can actively stop them from happening. They automate compliance.
And third, it all comes together in the merge request. That security widget is the central hub. It's where policy is enforced, and it makes the developer the primary owner of fixing the issues they introduce.
We've established that this whole approach really pushes security ownership onto the developer, who's supported by all this immediate tooling. But here's the thought for you to carry forward. If every developer now has this instant visibility into the security impact of their code, does that knowledge alone fundamentally change the skill set that we expect from a software engineer today? Are we moving to a world where the security expert is purely a policy setter and every single developer is expected to be a basic security implementer? That's something to mull over. Thank you for joining us for this deep dive.